I'm here to introduce Brendan Smith, who is a PhD student at MIT, and he works on nanoporous membranes, specifically nanoporous silicon, for water desalination and several other applications. Brendan actually graduated from the Nanotechnology Engineering program in 2013, where he went on to start his PhD. And so he's done work in other places like Canadian government, in the research labs, as well as in our university with Dr. WUNC. So he's got a broad range of experiences, and I guess he'll address some of the skills that he uses at MIT and the broad range, or the diverse skill set that he's able to apply to real-world problems. So with that, I'll pass it on to Brendan.
Sure. Thanks, Jaden. And what Jaden hasn't told you is he actually worked in my lab for 8 months last work term, so I've got tons of stories about Jaden too after, if you guys want to hear. Mostly good, but if you have to leave, that's okay. So like Jaden said, my name is Brendan. Thanks everyone for coming out today. Really appreciate you coming here on a Saturday. I really kind of relish opportunities like this, not only to talk to a bunch of young, kind of up-and-coming scientists, but also to talk to people from Waterloo and especially the nanotech program. I really loved the program when I was here. Obviously, in the space of 5 years, you go through a lot of ups and downs, but ultimately I thought it was a really great thing, one of the most important things I've done for my career to date, to be here. So I want to talk about a lot of things in general today, kind of a bit about the grad school experience at the end. You guys can ask me questions about that. I've already had some good conversations today with people thinking about grad school potentially, so I can answer all those questions. But primarily I want to talk about when we're framing our nanotechnology-based research, which I imagine a lot of you guys are actually currently doing or going to soon be doing, either in undergrad or in grad school later on in your careers, how do we actually think about providing a real-world impact? We've actually heard a lot about that today. So some of the stuff I'm going to talk about might be a bit of a reiteration, but hopefully we'll approach it in a bit of a different way, this time coming from the grad school research perspective. So essentially I want to talk a bit about my research, which is the scalable nanofabrication of nanoporous silicon and other nanotechnologies for applications in water and energy. So just to get started, everyone here is very aware that there have been a lot of groundbreaking discoveries in the nanotech space and the materials science space in general over the last 10, 20 years. I just want to touch on a couple of really cool examples. This one is actually happening at MIT right now. So in terms of filtration membranes, the Karnick group in the mechanical engineering department, they're actually using single sheet graphene, so CVD, chemical vapor deposition, deposited graphene, defect-free graphene ideally, atomically thin, and they're actually poking holes using ion beams, you can see on the top right there, on the scale of about 5 angstroms in the graphene. And they're actually proposing to use this for a filtration membrane, and they've done already successful testing. One of the main applications, or the main kind of advancements I would say in the nanotechnology space has been not only the fabrication side, but also even more so I think the characterization side. So now you can see on the right side here, a TEM image of actual atoms in the graphene lattice. So this has been developed over the past, a capability developed over the past 5 years or so, this aberration-corrected transmission electron microscopy that's actually allowed us to see these atoms. And therefore, we can actually see what we're making and go back and iterate on this nanofabrication, these nanofabrication techniques in order to do better and better and iterate on our process and approach. So the end message here is characterization is just as valuable as fabrication in terms of knowing what you're actually doing with your fabrication processes. A second kind of cool application, aside from filtration, that we've been thinking about is thermoelectric devices. So thermoelectric in a broad sense is just a way of transferring heat energy into electrical energy. And this is something that's fairly desired by people who are generating a lot of waste heat, such as in car engines or larger scale power plants, for instance. You have a lot of heat escaping to the environment, drastically decreasing the efficiency of your process. So people are doing really cool work here as well. Here's just kind of a diagram of a manganese silicide nanoribbon that's being made by these authors down the bottom left. And actually the purpose of nanostructuring these materials and also using silicon is that you have an electrically conductive material, and by actually doing some nanostructuring, you can really limit the transport of heat or phonons across that material. And again, we can use some really advanced characterization techniques to actually image what we're doing and kind of correlate the nanoscale morphologies and properties to the macroscale performance in terms of, in this case, the thermoelectric effect. I just threw in the formula up there to kind of iterate. We want to maximize conductivity or sigma, electrical conductivity or sigma on the top there, and minimize thermal conductivity or rho on the bottom. So that's kind of the goal in that case. So we have these really cool, the moral of the story here is we have these really cool nanotechnologies, really great materials. We can now characterize them basically to any extent we want to do that. But how are we actually going to use them in society? So on the top left, or on the top of this slide here, we're kind of illustrating what we need to accomplish if we want to actually make an impact in the real world. So on the left we have this nanoporous graphene fabrication technique, and on the right we have a desalination plant in Spain, which I got to go visit as part of my PhD work. And this is kind of what we're trying to achieve. Kind of the gold standard of filtration is desalination. So you're taking out ions which are solvated with spheres of water, and they're about half a nanometer in diameter. So you have to have a pore size on that scale, which they can actually achieve with these graphene membranes. But you then have to take that single sheet, atomically thin graphene membrane, and you have to make it into a 40 square foot membrane, which you see in the top right here. The blue long tubes, those are about 10 meters long, 40 square feet of membrane within that tube. They're currently polymer, which are being used. And you have to do that about 1,000 times, and then you have one desalination plant. So this turns out to be extremely, extremely difficult. And that just kind of is a very good example of how we can't necessarily apply these small-scale, laboratory-scale nanotechnologies to large-scale real-world applications. And the kicker here is that when you write a paper, that's typically what you're saying. You're going to say, okay, we're going to change the world by making this new desalination membrane, which is going to go in this plant, and I've done this nanoporous graphene membrane to do that. But it turns out it's not really possible. So same on the bottom. We have manganese silicide nanowires, which are 10 nanometers in diameter, and you're doing specialized CVD to grow these things. You're not going to be able to institute these in these heat exchange plants, which you see on the bottom right. So I want to kind of iterate that we have to sort of rethink our approach to these big research questions and how we actually manufacture materials at scale, or nanotechnologies at scale. And this kind of comes back a bit to what Professor Bolovich was talking about with the quantum dot displays. We're talking nanometer precision over 10 meters in length or so in some of these cases. So how should we really be thinking about this? So I'll talk about this in a second with regards to the work we're doing in the Grossman group at MIT. And I'm not saying that we have all the answers, but we're trying to approach this in the sort of new type of thinking. You want to target kind of essentially now buzzwords, which kind of tell you they're buzzwords, but they're buzzwords for a reason. They tell you that you can actually do this at scale. So if you're talking about quantum dot processing, for instance, we can do solution processing, solution synthesis of these quantum dots. So basically, as large as your bath is, that's how many quantum dots you can make. So very effective scalability-wise. We want to do room temperature and room pressure. This means you save a ton of energy. You don't need a vacuum chamber. You don't need a 1,000 degrees Celsius annealing process. And you want to do self-assembly if possible. So when we assemble these quantum dots over these large scales, sure, we have to come up with processes which can actually deposit them on the surface equally, but then the quantum dots take care of a lot of that by actually self-assembling them into tightly packed monolayers or bilayers or trilayers. So drawing from an example from Professor Bolovich's actual work, again with these quantum dot displays, as you guys have heard and as you know, quantum dot displays are gaining a lot of traction in the industry, particularly for LEDs and now also for solar cells. So these are things that can actually be applied. I would say in terms of applicability to the real world, these are now technologies along with drug delivery approaches that have actually made the most impact so far and should continue to do so in the near-term future. And the key here is that we're thinking along the same lines as the processes, as the words I mentioned on the left here. So we're doing solution processing, we're doing sometimes spin coating, sometimes blade coating. We're just dragging a blade over the surface, much like that device you saw in the video in the last talk. And you're doing self-assembly and phase separation on the surface of your substrate here. So these are all very applicable means by which we can manufacture large-scale technologies, even though we're looking at the quantum level or the nano level. And this is just an AFM picture showing you that we have these massive monolayers. So this is a smaller picture, but we can do this at the scale of a meter, and we can have less than 5% standard deviation in terms of the particle sizes and the vertical displacement of the particles. So now I want to frame it a bit in terms of what we're doing in the Grossman group, in my research group, and stuff that Jayden worked on with me last year. Essentially, I haven't provided much on the slide here, but we addressed first an issue, and the issue is that current filtration membranes and current thermoelectric devices can't really cut it in terms of performance. A lot of the filtration membranes we're looking at now for desalination, other applications in food and beverage industry, and oil and gas filtration, these are highly concentrated waste streams, very high temperature waste streams, and the polymer membranes either can't exceed 100 degrees Celsius in their operation, or they foul very easily, or they're incapable of being used with harsh chemicals like chlorine, a very common water cleaning agent, which you would want to put in your water. So essentially we started there by identifying a problem, which you kind of heard all morning is maybe a good thing to do. And then we said, how can we actually get at this problem? And if we can use nanotechnology as a tool, will that actually help us? In this case, we think yes. So what we did is we identified a technique that can make very small holes, or nanopores, in material, in this case silicon, which we want to actually leverage to make these kind of a paradigm shift in the membrane space from polymer, something more like a nanoporous ceramic membrane, which I'll tell you a bit more about. So the way we actually do this, I'll explain the process real briefly. It's kind of a little diagram on the screen here. Your blue is your silicon. You have to deposit some kind of noble metal catalyst, be that gold, silver, platinum, what have you, on the surface. We usually use gold. Jayden explored some other materials as well. That's basically all you have to do. At that point, you then immerse your substrate in a solution containing some nasty things like peroxide and HF. The peroxide is actually reduced to the surface of the gold particle. This is injecting your hole, so it's sort of an electrochemical process. injecting your hole into the gold, which is in turn injected into the silicon, oxidizing the silicon. And you're etching away that oxide that's created locally around your particle catalyst using the HF. And it turns out to be a continuous process in that you're actually attracting the particle to the bottom of the pore as that pore is created through van der Waals interactions. So the particle kind of acts as your nano drill bit, kind of self-directed going down through the silicon in a very anisotropic fashion in line with the crystallography of the silicon. So the good things about this technique are you totally avoid all the pain points of lithography, E-beam lithography, for instance, which can make similar type structures, but you can do this at a much larger scale, all at room temperature and pressure in a solution type process. The other advantage is that, I guess coming back to lithography, even E-beam lithography, you have intrinsic limitations in the resist that you're using, in the radiation source that you're using, and how small a feature size you can make. In this case, we're actually etching pores which are very similar to the size of the initial gold particle, and that means as long as you can get a 1 nanometer particle, you can get a 1 nanometer pore at aspect ratios of up to 2,000 to 1. I'll show you some images in a little bit. This is a very exciting potential when you compare it to standard lithography-based techniques. So here's a TM image of our work. This is about a 2 to 3 nanometer particle, etching a 2 to 3 nanometer pore. So this is a top-down image. The lighter part in the middle is the pore that we've created, and the darker part is a thin silicon membrane. So this shows the kind of scales we can operate at. If you look closely, you can kind of see the silicon lattice. I'm not that great at TM, but I'm working on it, so we'll get there eventually. The bottom is a focused ion beam cross-sectioned pore. So this is a much larger pore, about 200 nanometers. And in turn, this is created by a 200 nanometer gold particle. So you can see we have very close correspondence to the particle size and the pore size, which is one nice thing about the technique. So what I've kind of learned through this process through my first 3 years of my PhD are that the scalability and the control you can have over your process are often inversely related. What I mean by this is if you have a process which you think is super scalable, I can make this as large as I want into a factory-sized processing line. But if you don't impose certain controls and be very creative about how you're approaching the process, you're going to have very poor controllability over the process because due to the very kind of scalable nature of it, it means that you're not able to impose a lot of control. So kind of case in point, the process we were initially looking at, kind of the state of the art of this developed technique, was that you just kind of drop coat your gold particles on the surface, and then you do your metal-assisted chemical etching. And this kind of gives you a whole array of possible outcomes, essentially, which took me a year and a half to kind of go through. The first kind of number one there is that you actually get very effective etching. So you get your particles on the left translating to pretty nice vertical pores in the silicon. But that's kind of a minority in terms of the frequency of these results that you see. The second is going to be kind of large-scale clumping of the particles, and this actually forms very large pits in the silicon, which you can imagine is extremely detrimental for any kind of filtration process. Anything you want to filter out with these pores is going to go right through that mess on the bottom left. Number 3 here is lateral etching. So although this is kind of controlled by the crystallography of the silicon, which you can control very well, as you probably know, sometimes if the particles go off to the, for instance, in the 101 direction, they're just as likely to go that way as the 100. So there is some preference, but part of the process is indeed sort of random. So we have to figure out a way to control that as well. And then finally, sometimes you just don't get good etching altogether. So number 4 here is a good example of that. And that has to do with the way the particles are sitting on the surface, essentially, before you start your etching process. So Jayton and I worked on this for 8 months, and we kind of figured out a way around some of these issues. And it turned out to be a very simple one, which I want to kind of state is clearly preferred over some kind of complicated electron beam lithography type method. It turned out all we really needed to do was actually encapsulate the particles in these SiO2 shells. So by doing that, not only could we space out the gold particles on the surface and actually prevent them from interacting with one another on the surface, we could actually form nicer morphologies of monolayers very easily. So you can see here we have a nice monolayer, not close packed, but at least not overlapping with each other, and effectively isolating the gold particles. So you can see silica shell around the edge and then the dark gold core in the center. And this can be, there's been a lot of work done on doing this over large scales. So here you see, I wouldn't call this large scale, 10 microns across. Really the only limit here is kind of how large a deposition setup that you have to deposit these particles on your wafer. And then finally, you get your etching. So we've done a lot of characterization on the product here. And compared to, I would say, the bottom left here, you get something much better in terms of pore dispersity on the surface, as well as pore sizes. So again, Jayton did a lot of work on characterizing the pore size here. And you can see that you get pretty sharp pore size distributions over large scale. Diameters, in the case of 5 nanometer gold core particles, you can see diameters of less than 10 nanometers. The reason you get slightly larger pores than particles is because the pores actually enlarge over time. You do get a little bit of etching of the pores even when the particles aren't present. And then another image that Jayden was working on as well. You can actually do this on kind of the macro scale in that we have centimeters wide membranes now, which we're about to start testing very soon. So the next step, even after you've considered the scalability of your process, you have to think, how are we actually going to integrate this kind of material into an actual device? So clearly with a thick silicon wafer of 500 micron, you're not going to make a membrane out of this. And the reason for that is your permeability is going to be so bad because the water has to go through such a long kind of length scale. So we're trying now to thin down these membranes to the point where we can actually flow water through them at very high permeabilities. And you can see here a cross-section of some silicon that we actually first thin via chemical etching and then etched through with these SiO2 gold core nanoparticles. So kind of hard to see because the length scales are so incompatible, but the membrane obviously is here, and then these long streaks are the pores. So we have some variability right now in the actual pore size, and we've yet to actually test the permeability of such a membrane, but the next step is going to be to optimize the thickness along with the mechanical resilience of the membrane, resistance to these applied pressures, and how much water can we actually flow through there, and what also can we reject from the initial feed stream given a certain pore size. Just to kind of wrap up, kind of the whole way along the way we've been considering how are we going to actually integrate this into a real process. So our thought is something very simple yet hopefully effective. You start with your stock silicon wafer. We then thin this in a very simple chemical mixture, so you can thin this controllably to the scale of 1 to 5 microns in thickness. From there, you can do your metal-assisted chemical etching with the gold particles, which I discussed, ideally the SiO2 gold particles. And then you do the etching, which leads to this thin nanoporous silicon membrane. And the very important part, which we're just starting to do now, which is very exciting, is the actual testing of this membrane on a lab scale. And that's kind of the first time that you know whether or not your assertions have been correct in terms of a hypothesis that this will be a superior membrane. So here what we're looking for is we're testing permeability, we're testing anti-fouling capabilities, we're testing thermal resilience, and we're going to benchmark this against the current state-of-the-art polymer membranes, essentially. So that's what you really have to do if you want to prove an impact in the real world, is benchmark against the current state-of-the-art technologies. And the other important thing, which was sort of mentioned today, is actually going out and talking to people who will be using this. If you think of this as a product, if you're an entrepreneur trying to actually sell this to someone, what are people interested in? Do they care about fouling? Do they care about thermal resilience? Do they care about chemical resilience? So what we've actually done is we've actually gone out to these people in the oil and gas industry, the food and beverage industry, and talked to them about what their current pain points are. And that's actually allowed us to structure our research much more accurately than we otherwise would have. It would have been a lot more nebulous and kind of like playing pin the tail on the donkey blindfolded, essentially. So what we've essentially done by talking to the industry people is taking off that blindfold and pinpointing those kind of benchmarks which really matter, I would say. So even when you're undergraduate research, you can definitely reach out to people who would be potentially using these technologies to get a really good idea of what's actually important in the space. And real quick, just another kind of approach for thermoelectrics. These are actually, there's less requirement here for scalability because thermoelectric devices are usually a lot smaller. Filtration, we're talking many tens of meters, whereas thermoelectrics are more kind of hold in the palm of your hand device scale. So sort of a similar thing. You start with P-type and N-type. You do the metal-assisted chemical etching process, and then you assemble this very simple device, which could serve as a first proof of concept for what we're trying to achieve. So that was all pretty fast. Before I wrap up, I just want to give you some general thoughts on grad school, as I know a lot of you guys are thinking about that right now. When you're thinking about, I didn't put school on here. School kind of sorts itself out by virtue of being admitted to a school. But when you're thinking about priorities in terms of what you're going to do, your research, your advisor, I would certainly prioritize advisor almost above all else. The reason for that is you're going to spend 4 or 5 years with this person, and they're basically going to be your boss and essentially kind of your collaborator in terms of your research. So if you pick an advisor that you love and a project that maybe you don't like so much, there's going to be plenty of room to be able to pivot on that project. I've already done it a couple times. Most people I know do not go through a PhD without pivoting at least once or twice. So you're certainly going to change your research approach over the 5 years. You can't change your advisor. And if you end up actually changing your advisor, it's a very long and kind of arduous road. So definitely prioritize the person you're working with even over the work that you're going to be doing. And then finally, the program. So I'm in materials science at MIT. There are people in my lab working for the same advisor who are from mechanical engineering, from electrical engineering. So that doesn't really matter. The boundaries nowadays are so kind of blurred that you can work on a whole range of things, being from any department that you are really interested in being in. So that's kind of the last stage of importance. I've heard a lot of concern about becoming over-specialized doing a PhD. that can happen to you, and in some cases you might want that to happen if you want to be a faculty member at some point, but it'll only happen if you want it to happen and if you let it happen, and if your advisor lets it happen. So personally, I've taken the approach where I want to work on both the nanoscale of my material, but also all the way to the application stage. So how do we characterize on the nanoscale using TEM, SEM, focused ion beam, all that stuff? How do we improve the process and develop a new solution-based chemical etching approach? And how do we use that approach to then actually fill the application need? So for me, I've actually addressed it in a very broad manner. That's probably not well suited for, say, a faculty position down the line, but I don't want to go there. I want to go to either startup or industry. So it's kind of all about how you frame it. And there are tons of opportunities at places like Waterloo, MIT, all the other big schools, where you can do a million different things, like, for instance, organize your own conference like this one. So these are all things that kind of contribute to your brand and the full package that's going to be you down the road when you're applying for faculty or industry positions. So definitely take advantage of all of that. And I think that's about all I need to say. I think we might have time for some questions, but thanks a lot for listening, and I'm happy to talk to anyone now or later on.